from what Sasha discussed 2 days ago. There will be a mini recap in case you forgot what was said. Let me preface this by saying that I am a theoretical physicist. I don't consider myself even a mathematical physicist. It's full of mathematicians here, so apologies for the lack of rigor. This will be a talk given by a physicist. I try to think of, the kind of things that might be for granted and might not be obvious for a mathematician. So I try to explain a few extra things, but if by any chance you see something you have no idea what I'm talking about, and I'm talking about it like it was something very obvious, please stop me and ask me questions. In my mind, mathematicians ask fewer questions than theoretical physicists, but I'm happy to be proven wrong. So please ask questions. So Sasha told you the things we already understand, and I'm gonna tell you some things that we're understanding now, but I will focus also on the open questions that we have, on the things that are not completely understood, but we sort of see a path towards them. And this is in collaboration with Sasha, who's here, Barak Gabay and Victor Gorbenko, who are at EPFL, and Jiaxin Tiao, who's in Tokyo. Okay, so let me remind you first of all why we are doing this. The reason is that for a physicist, symmetries are a great tool. Symmetries are nice because they really save a lot of work. We don't need to compute as many things when we have symmetries because we will know that some of these things will be, for example, zero. Like we're interested in correlation functions in CFTs. And if we have a symmetry, we can sort of already say, oh, this correlation function is zero. We don't need to compute it. In some other cases, which will be this case, when we have some continuous symmetry, we have word identities, and word identities, they tell us that some correlation function is equal to some other correlation function with some number that we know in between. So we need to compute fewer things. So we love it because it really saves us a lot of work. And the question, which is related to a lot of progress that has happened in the past decade or something more in the field of QFT, is that we've understood that symmetries, as we understood them in the past, was sort of a very restrictive view on symmetries. We understood that they can be thought of it in a more general sense, and there's this field called generalized symmetries, which brings us to the question. We've seen a lot of this progress, but have we finished it? Have we exhausted all the possibilities? Are we missing something? And this was the question that brought us to this paper, which was, what is the most general symmetry that I can have in a QFT, and in this specific case, in a CFT? So we've argued, and hopefully in a convincing way, that quantum group can be the symmetry of a CFT. The reason why we think this is the case is that there's lattice models, so a spin chain or some statistical StatMech model that has quantum groups as a global symmetry. And these models are critical. They're critical, which means that their long distance physics is described by a continuum theory, and in this case by a CFT. So given that the CFT is describing the physics of this model, then if this model has quantum group symmetry, so should the CFT have. And we know that there is some lattice system that have this symmetry. I will tell you the details about them. And therefore, we expect CFTs to have this symmetry. And this is what Sasha told you a couple of days ago, what we expect from these theories in general, and then you consider one example where we studied this. And this example was coming from the continuum limit of a lattice system. So let me start with a very small recap of what Sasha said, for those of you that were not here, or for those of you that like to hear a recap. And then I will tell you, I will look at the continuum by starting from the lattice. Hopefully you will see why I do this by then, and then I will discuss some interesting boundary conditions that we have studied. Okay, so we start with the mini recap of what a quantum group is. And normally when I talk to physicists, that's the whole of the talk is discussing what a quantum group is, but here this should not be the case. So let me remind you, in any case, we're considering the UQSL2. We have three generators, E, F, and H, but we like to work with Q to the H. And E raises the eigenvalue of H by 2, F lowers the eigenvalue of H by 2, and the commutation relation between E and F gives us the Q deformed version of H. And Q is some parameter that I'm free to choose. The nice limit is taking Q to 1, where I recover the SL2 or the SU2 commutation relations. Okay, the interesting thing for me as a physicist is that the coproduct is weird. So I care about a coproduct because if I know how the algebra acts on a spin or on an operator, then the coproduct tells me how it will act on two spins or two operators. So specifically in a correlation function, I will want the algebra to act on many operators. And to do this, I will need to use the coproduct. And given that I've taken the SL2 commutation relations and I've deformed them, and given that the coproduct should be compatible with the commutation relations, so the coproduct of some commutator should be equal to the commutator of the coproduct, I need to change the coproduct as well. So I can now have the usual SL2 coproduct. In this specific case, I will make this choice. So the coproduct of E is E times 1 plus Q to the minus H times Z. So this is the thing that is quote unquote unexpected if you're just coming from SU2. The coproduct of F instead has this Q to the H here, which is expected. And then the coproduct of H is just H times 1 plus 1 times H. Okay. What I will need is also the representation theory of UQSL2, and I only care about, yes.
So are you thinking about Q as like living in a disk or something, living in the disk or something? Or
Eventually, I'm going to take Q to be a phase, but what I'm saying so far doesn't care about it. I will take Q, well, to my knowledge. Q, I will take it to be a phase. And I will take it to be not a root of U. Okay. So I'm interested in physics. I want operators and states and so on to transform in some finite dimensional representation of the algebra I have. So I care about this representation of UQSL2, and there's two different situations which, in order of difficulty, the simple case is, the easy case is when Q is not a root of unity, and the hard case is when Q is a root of unity. Thankfully, we're only going to do the easy case today. And here, representations of UQSL2 look the same as those of SU2, as in representation that are labeled by a half integer, the spin, a non-negative half integer, and this n labels the different states within a given representation, and it goes from minus L to L. So it's like a spin L representation in SU2. H reads off the eigenvalue m from the state, and E and F, they raise and they lower the eigenvalue, the m labeled by 1. So E raises it by 1 and F lowers it by minus 1. So I build the representation by starting from some highest weight state that's filled by E, and then I act with F many times until I hit the lowest weight state. And then that's it. So it really looks like SU2. The only difference is that, well, the dependence on Q is in the things that I haven't written. Here there would be some matrix element that I haven't written, but that one depends on Q. The rest is all the same. If I were to take Q to be a root of unity, then this would fail in some situation, and I'm not going to do that. So today is going to be an easy thing. Okay, so this is probably the things that many of you knew. But now let me go to the world of CFTs. The setup is that I'm working in 2 dimensions and I'm only considering Euclidean space. Q is going to be a phase. And I would like my theory to have this quantum group as a global symmetry, which for me means that it commutes with the space-time symmetry. So the generators of UQSL2 commute with the generators of BSL. And I would like the symmetry to do something. So operators transform under the action of UQSL2, and operators therefore will have the labels of the quantum group beyond the usual label that an operator will have. For example, the weights under Virasoro. Operators will also have L and M that denote which representation of the quantum group they're transforming. Now, what I'm interested in at the end of the day is correlation functions in a CFT. Yes?
So when you say Euclidean, do you mean like genus, like you're just working in genus 0, basically?
Yes, but like, okay, maybe this is, but Euclidean, it means that there's no time. So maybe this is a thing for physicists, but yeah, I'm gonna be on play for the beginning. So I want that correlation, I want that word, so I'm interested in correlation functions, and they should satisfy word identities, which means that I take some correlation function. This should be an n, not a 2. And this x is a generator E, F, or H. And this x on this, you can make it act on the left, and it will give you 0. And the fact that you can also make it act on the right using the coproduct will tell you something non-trivial about some correlation function. So this is something that this is not super explicit, but Sasha had a very explicit formula. Okay. And using this directly, you can see already something very important. And this is related to the fact that we will deform the coproduct. You see that this already implies the lack of mutual locality between these operators transforming under the quantum loop. So just by using the word identities, you see that the correlation function O1, O2 is different than the correlation function O2, O1. So here, I'm not moving the operators in space. I'm just swapping them within the correlation function. And, we are physicists. We think that when things are, I don't know if this is, if people know this language, but I'm gonna say, when things are space-like separated, you can permute them for free. And in Euclidean space, everything is space-like separate. So here there's a plus or minus, because if you were working with bosons, you would have a plus. If these two operators were fermionic operators, you get a minus. But what we find is that you get a more complicated number because of the word identities. You see directly from there. Okay, so I would like to think of these operators as living at some point x and some point y. But if this was the case, then I would need to, this mutual locality condition would need to be satisfied. Should be able to take operators, move them around, things would behave nicely. But here we lose this locality that we all love. So we need to change our approach to these operators. They cannot just be living at some point x. The minimal amount of non-locality that we have to introduce, and that turns out to be enough, is that the operator is living at some point x, but it has a topological tail. So there is some line that ends at the point x, which is topological, so you can move it around easily with no, without changing anything, as long as you don't cross other operators. So this picture makes you understand why a correlation function that has like O1 and O2 in this order is different than a correlation function that has O2 and O1 in this order. Because one, you could represent it, for example, with these two lines in this configuration. And the other one, you would represent it with these lines in this different configuration. And given that you can move these lines around, but you cannot make them cross operators for free, then these two things will not be the same, in the same sense that these two things will not be the same. So this is what we propose in the how to make sense of this theory that has this peculiar symmetry. And then we go and check this thing, because of course, otherwise it would be a pretty empty statement. So we consider it in a specific case that I will discuss a bit more later, as in a CFT where we had the spectrum that has a quantum group symmetry. We checked a couple of things. The first thing is that there must be some relation between the UQSL2 spin, so the representation of UQSL2, and the space-time spin. The reason you can think about it is from this, you can move operators around and then use the R matrix to swap these two lines so that you go from the first configuration to the second configuration, for example. And the fact that you can do these two operations gives you some constraints. So the things that you do, you can get to the same configuration in two different ways, and those should agree. And this will give you some relation between the space-time spin and the UQSL2 spin. And in this theory that we consider, this is satisfied for all operators. And the other thing is that despite this theory being a bit of a weird theory, a bit of a peculiar theory, we want it to be well-defined. And one of the things that we want in CFT is that we have crossing symmetry. So crossing symmetry means that we have an OPE and that's associative. And this, we checked that it's the case, so we needed to compute 3-point functions in the CFTs. That was not known, but we did it, and we checked that indeed that the theory is crossing symmetry. So, okay, so this passes. Our proposal of how to make sense of these operators appears to be consistent. And first of all, I will ask if there's any question so far. Yes.
Does it also make sense in higher genus? What you do with a string?
Yeah, we haven't thought of that much, so I'm not sure. Yeah.
For fermions, you can either think of them as local operators that anti-commute, or bosonic operators with a string that
Yes.
also makes them anti-commute. Is there a version of this for these? Is there some kind of quantum group type operator that is local, but that still satisfies the computation relations like you want?
So one thing that, let me answer a part of this question, but not the whole thing. One thing you can see is, for example, when you observe these theories, that you actually, the spectrum of the spin is not a half integer. It's just some random, like some number. It's so from that point of view, it looks like it's worse than that. But then I'm not sure about I'm not sure I understand completely your question.
I suppose, yeah, we know that in 2D you fermions and bosons, you can get anyons, right?
Yeah.
They'll think of as local. Is there some kind of way? It's like we say, okay, fermions are actually local if you express these things as fermionic operators.
Yeah, so there will be operators that within, like with respect to each other, they are mutually local. The statement is that generically, operators that transform under this quantum group will not be local with respect to each other. But then you could find a subsector within this, this space of operators so that they're local with respect to each other. But the thing is that even when taking like the same multiplet, different operators of the same multiplet will not be local with respect to each other. So
here you talk about full CFT. If it's CFT,
it's a CFT.
Correlator for full CFT.
Yes.
It's not chiral.
No, it's
not chiral.
Yeah, it's not chiral.
Can you go back to your picture with the lines?
Yes.
So you sort of draw the lines as going off to infinity, but if you do
Yeah.
CFT, there is no infinity, right? So you have to
Yeah, that's I was trying to sweep it under the rug for now, but there will be either, for example, some defect, something on which these lines end. That's actually what we'll have. I might have some boundary, but I will tend to have something. What we have actually is a construction using some Coulomb gas formalism where they end at a point, and then the correlation function is independent on the position of this point.
So it's
So
like
this-
a weight 0,0 field, the point, or
Yeah, something like this. So what matters is the ordering of these things, but like from the purely CFT point of view, like this point could be anywhere you want. It's not special. Then in practice, the Hamiltonian, the lattice Hamiltonians I will give you, I think they clarify a bit this thing because you have some sort of the insertion of something at some point, which makes it a very natural place for these lines to end. Okay.
From the point of view of inserting this point where the lines end, wouldn't you suggest that it actually can be defined also on higher genus?
Yes, probably. Okay, so I told you some things we understand. What are the open questions? Otherwise, what else could I talk about for the next 45 minutes? So as I said, we have the conformal data of some of the CFTs. For example, we have the weights under Virasoro, we have the OP coefficient. So that in principle tells us that we can reconstruct any correlation function of local operators. So, okay, that's a lot of stuff. But we don't understand some things about this operator. We've been very abstract about these operators, and we would like to understand some things. For example, I told you that we have some topological lines, and maybe I would like to understand what these lines, where they come from, what they're made of. And clearly this requires some sort of microscopic description, but as a physicist, that is something that I would like to have. And often it clarifies some things. For example, what if I take this line and I fuse them together? Right now, I don't know what's happening. So if I have some microscopic description, I can look at this way more explicitly, for example, and try to understand this. would like to understand this in terms of topological defects. I would like to understand also if these CFTs are related to other CFTs that look very similar, but not exactly the case. So in order to do this, I will have my approach as a physicist. So I care about CFTs because they describe the long range, the long distance physics of some lattice model, which is critical. So for example, you take a piece of iron, you go up to 770 degrees, that's the Curie temperature, stops being magnetic. At that point, it has scale invariance and it also has conformal invariance. That's why I care about CFTs. Other people might have different ways of thinking about CFTs, that's fine. But given that this is why I care about CFTs, the way in which I'm going to study CFTs is by studying a spin chain, which is some lattice model, which is critical. So this spin chain will have a UQSL2 symmetry, it's critical, and in the thermodynamic limit, it will be described by a CFT at long distances. So this is what I'm going to do. It's going to be very, very concrete. I would like to study something really like pull my sleeves up and go and look at it. Okay, so now this motivates me to go and consider some lattice system. I'm going to consider the following. Well, let me tell you the relation between lattice and CFT in a sort of more explicit way. So I tell you that the long distance physics is described of a critical system is described by a CFT. What do I mean exactly? There's two things that I'm sort of interested in, more the second than the first, but the first one is also something important to know. So let's say you take your spin chain, for example, on a circle, and you go and look at the energy levels of the spin chain. So you have a Hamiltonian, you diagonalize it, you see what the energy levels are. This computation tells you what the CFT scaling dimensions are. So if you take the energy, the energy of excited states and labels the states, and you subtract the ground state energy, this, given that the system is critical, it's a gapless system. So this in the thermodynamic limit, as n goes to infinity, this goes to 0. But if you divide by n, what you find is the scaling dimension of the operators of the CFT. There's a v in front. This is like the speed of sound, if you want. This is something that depends on which specific Hamiltonian you take to study some CFT. So for example, by studying the energy level of a spin chain, you will find the scaling dimension of operators. That already tells you something. We're going to be more, this is actually how we knew some of the spectrum of the CFTs already. We're interested in something slightly more complicated actually, which is correlation functions. So the idea is that in the lattice system, you can, you compute the ground state, you build some operators that's sitting on some site I or around some site I, and another one on J, and you compute the 2-point function on this vacuum. And then you take the distance of these two operators to be larger, quite large. And as you take this distance to be larger, you see that this correlation function decays as a power. And there's a leading term, and then there will be sub-leading terms and so on. So this leading term, when you read off the power of this will tell you what the CFT operator dimension is. So this will tell you, for example, reading this power here, will tell you that there's an operator in the CFT whose scaling dimension is exactly the same as that one. So if you look at this operator at large enough distances, it will look like the CFT operator. And of course, there's infinitely many operators. Indeed, there's many terms here that I'm neglecting. So I first could read off this power, then subtract something from this operator so that the leading term is actually this one here. And this will tell me what are heavier operators and so on. So this is the sort of things that I'm interested in. Any question on this?
Spin chain, or do you do a statistical lattice system?
Spin chain.
So theta I just on Pauli matrices, basically.
There's no theta yet. That was a fancy O, but there's going to be many sigmas in a second. But yeah, this would be, okay, if you have a spin chain, you will your thing out of, but this is more general. You could have a different lattice system. Okay, now it's time for Pauli matrices. I am going to consider this spin chain. It's studied by these authors. I'm going to refer to it as the Pascal Hamiltonian. I have a one-dimensional spin chain with n sides. And on every n side, I have a spin hat living on site. And the Hamiltonian is given by the following. So this sigma x, sigma y, and sigma z, they're the Pauli matrices. And I have a bulk term. So this is, I'm summing over everything in the spin chain, which is what we normally call XXZ Hamiltonian, if you're familiar with the term. But you have some sigma z, nearest neighbor interaction, some sigma y, nearest neighbor interaction, and then some sigma z, nearest neighbor interaction, where the coefficient, now it's different. So this one, that's why it's called XXZ. So this one, I will parameterize it with this Q. And then this I will call, if it was only this, I would call it XXZ spin chain. But I'm gonna add this other term here, these surface terms. So here they have this q to the minus 1, so this minus will be important. And then this is just a one-body interaction on the first and on the last side. So it's a relatively small thing. I could have a very long spin chain and just adding some interaction on the first and on the last thing. Okay, this is symmetric under UQSL2. How do I see this? I see this by writing explicitly the UQSL2 generators. So H will be just the sum over the sigma z's on overall sides. So my Sasha told me that I should draw pictures, so I've drawn pictures, but H is not a very interesting picture. It becomes a bit more interesting with E, where this generator is a sigma plus. So sigma plus is, okay, sigma x plus I sigma y over 2. It's this operator sigma plus, and then you have a string of q to the minus sigma z to the left. And I'm summing over this position I. So I would draw it like this. There's this operator living at a point, and then a string to its left. And I'm summing over this. F, the lower end generator, is similar. I have a sigma minus at point I, and then to its right, I have a q to the sigma z. So it's here I have a minus, here I have a plus. This is to the left, this is to the right, but the idea is sort of similar. So you write down these operators very explicitly for any value of n, where n is the dimension of your spin chain, and for any q, and you check first of all that they satisfy the UQSL2 commutation relations.
Can I ask a question?
Yes.
Sorry, I'm supposed to know this, but can you tranquilize me, please? So I'm adding this magnetic field on the boundary of the spin chain.
Mm-hmm.
So I would expect that the bulk physics should not be very sensitive to this.
Very good question.
And so
I will tell you something about this later.
Yeah.
That's a fair thing to think. So why should the conformal data be different?
Well, I understand that the opens, I understand that this energy spectrum can be different, but the bulk physics in some sense should be invariant. I mean, for example, if you consider bulk correlation function very far away from the boundary, I mean, shouldn't this be somehow independent from this boundary term?
It's a good question to keep in mind. I will say something about this in a bit.
Okay.
And then, but I agree that's the physicist's intuition, is that this is a very small thing to do. If I have n equal a billion, why should I care?
It's non-unitary, right? Because it's
Yeah.
I sine, right?
Yeah.
Because of non-unitarity.
I think it's related to the fact that it's non-unitary. This is Q is going to be a phase, so this is going to be non-unitary. Well, so the Hamiltonian is not going to be a Hermitian. I will say it.
The central charge will change, no, when you add this from C equals 1 to.
This is a thing that I've argued with many people about. Some people are here today. Central charge depends on what you mean by central charge. There's different, there's a central charge and an effective central charge, and I call something central charge, and some people call that effective central charge. In my mind, this doesn't affect the central charge, but then it will affect the effective central charge or something like this. So
Depends what you call the vacuum.
Yes. There's an issue with this language, but in one of these two definitions that you have, this will be changed. So for example, if you go and compute the entanglement entropy, that should tell you what the central charge is. This will not affect it by itself.
But without term, you will not have UQSL2 symmetry, right?
Yeah.
So it will be very different CFT maybe.
Yes. Yeah. So there, in some other sense, yeah, exactly. It's like placing some operator somewhere, and it changes the central charge, or the effective one, depending on the language.
Maybe if you don't add this term, what is the physics of this system?
This is the free boson at some radius. like the XXZ renormalizes to some free boson at some radius with the radius is given by Q. Like it's a function of Q. So yeah, it's gonna be pretty different. Okay, so I said these things are they are the generators of UQSL2. You check it explicitly, you find those commutation relations, and then you see that it commutes with the Hamiltonian. So that's what we mean by saying that it has a symmetry. It commutes with the Hamiltonian. So to give you an idea of the physical consequences of this is, let me fix n, the number of sides to some value, let me fix q, and I just diagonalize the Hamiltonian. And I plot the energy levels. These dots are the energy levels. I will see, for example, that the lowest energy level is some singlet, so just sitting by itself. But then as I go higher up in the spectrum, I will find 3 states that have the same energy, but are a different value of SZ. SZ is, it's the eigenvalue of H, SZ. So these states, they form a spin 1 multiplet, and you go from one to the other by the action of E or by the action of F. And the fact that they have the same energy is related to the fact that this commute with this. And as you go higher up, you will find a spin 2 representation with 5 sides, a spin 3, and so on. So this is the kind of physical consequence on the model. You have a question?
Yeah, I think so. So can you say what's the like vector space on which these things are acting? It's like a vector space spanned by some these thetas or something.
Like the Hilbert space.
Okay.
Yeah, it's just like spin half on each side and just the tensor product of this.
Show my duality. It's a square, you take fundamental representation tensor n times.
Yeah.
You have like a product.
Okay. Okay.
Okay,
so this is everything I said is,
So is this something extremely like rare? Should I view it as something super special, or is it something that will occur?
UQSL2?
Yeah.
I don't know, are symmetries special or are they a common occurrence?
I don't know. I think spins have rotation symmetry. So if you put them together, like, is it hard to cook up Hamiltonians which have the symmetry? Is it something which was cooked up, or is it something natural?
I don't know how to answer. Well, it's not something I'm used to, so I wouldn't call it very natural. But you can build them. I don't have a
different way of phrasing the question. Can you write down 10 more Hamiltonians, which also has the symmetry?
I can write many Hamiltonians by taking this one and deforming them, for example.
So this
Yeah,
one is
in
easy.
terms.
You take Casimir of SL2. Act on by Casimir, take a product of Casimir, act on neighbor sides, and sum this over.
Okay.
From 1 to n.
Huh?
This is what you get.
This is what I get?
Yeah.
Okay.
Same. So it's Casimir case, like local interaction given by action of Casimir on neighbor sides. You take any quantum group, Casimir, act on any tensor product, you get a quantum invariant.
Okay.
Maybe that answers.
Maybe one thing to say is this was constructed without reference to QSL2. It was just to be integrable, and was later realized.
Yes,
as
yes.
quantum groups.
Just true, yes.
Okay, so I talked only about the lattice so far. I'm not saying anything about the CFT. Now the important thing is that this model is critical for Q a phase. So when Q is a phase, it's critical. And I would like to build operators on the lattice that become the CFT operators in the thermodynamic. So to do this, I require 2 things. One is that these operators, they transform in a multiplet of UQSL2, spin 0, spin 1, or so on. And that these correlation functions on the lattice, when I take them at large enough distances, decay as a power law. And I'm going to do this numerically. But let's check first the first thing. The first thing is that, let me remind you what the story is for SU2. So in SU2, I will have, again, so this is just the Q to 1 limit. I have operators, they also have the L and M label, of course. And the action of the generators is given by the commutator. So when I say H acts on O, it's the commutator between H and O. And this, for example, H will read off the value M from the operator. E and F, they will, as I said earlier, raise the value of M by 1 or lower the value of M by 1. So for SU2, this is a very well-known thing. Again, I should draw a picture. So the way I represent the commutator of E and O is, well, one term will be O first and E later, and the other term will be E first and O later. And then given that E is topological, I can put these two things together into E circling O. And this is just the action of the charge E over the operator O, and it tells me OL n+1. So, okay, this is the action of the operators. Now let's say I want to build a spin 1 representation. The way I build it is, well, the result is very simple. Sigma, the Pauli matrices, sigma plus, sigma z, and sigma minus at a given site, they form a spin 1 representation. So you see this because sigma plus is the highest weight operator, so it's killed by E, and then you lower it with F, you get sigma z, then you lower it again with F again, and you get sigma minus, and then you see that this is a lowest weight operator. So this is your spin 1 operators for SE2. Now we want to do the same for UQSL2. Things are a bit different because the action of the adjoint action on operators cannot be the commutator like it was in SU2, because the commutator implies a trivial coproduct. So this is just a statement that the commutator between X and O1, O2 is just the commutator of X on O1 times, nothing acting on O2, and then the one O1, and then the commutator acting on O2. So this is what I would write like this in commutator language. Here, I need to have something different, and this is just known. The way in which I should consider things is that the adjoint action of E on O is not just the commutator, but in this term, I sandwich O between Q to the minus H and Q to the H. So if you get rid of this Q to the H and this Q to the minus H, you just recover the commutator. But now we have this extra term. The adjoint action of F is the commutator of F and O with this Q to the minus H, and then the adjoint action of Q to the H is the usual. Okay, so this, by the way, this depends on which coproduct I chose, and given the coproduct that I chose, this happens. So if you take this, for example, then you can check easily that the adjoint action of E on two operators is the adjoint action of E on the first operator, and then the adjoint action of E on the second operator, where O1, though, it's being sandwiched by some Q to the minus H. So this thing here is the adjoint action of Q to the minus H. So you can rewrite this like this. And this is simply the coproduct E times 1 plus Q to the minus H times E. So this is the thing I want because it has the coproduct that I want. And now I can look for operators that are in a spin 1 representation, which are killed by this adjoint action of E, and then they're lowered by this adjoint action of F until I hit the lowest weight operator. So before I do this, it's time for pictures. So the action of E was just writing things in SU2. It was just circling operators by this E line. Now, again, if I only were to draw this E line, I would, without anything, I would recover the trivial coproduct. But let me write, this is gonna be a bit different. So E is the sum of, if you remember, the sigma plus at site I and a Q to the minus H line to the left. And given that I'm summing over this, I'm gonna draw it in the following way. So there's this green line that's attached to this red line here, and I have to remember that I'm summing over this. So the action of E on some operator, O, as I was called out before, I'm completely neglecting what's happening to the left of this, but this is enough to see this. So I'm gonna represent the adjoint action of E like this, because if you think about this, the green line is topological, the red line is topological, I can write it as two terms. So first, the term where this line is just above the operator, and then the term where the line is below the operator. But as you see, I need to take care of this red line that's coming along with the right for E. So here is just above, there's nothing to worry about. Here instead, I have to wrap it around the operator to go back to this, because it still needs to be attached to E. So now okay, the left-hand side I'm satisfied with, but here I can just, given that this red line is topological, I can send this to infinity, and then I recover something like this. So I have the line that's basically wrapping around O only, and then and then there's something else. So the red line, it's Q to the minus H. So when it's acting on some operator, it will give me Q to the minus H acting on this operator, which is this. So I can get rid of this line by considering this term here. So this figure becomes this other figure, and now let's look what I should have here on the right. This is E times O. So I first had O and then I had E. That's great. And here instead of Q to the minus H, O Q to the H times E. So first I have E, and then Q to the minus H, O Q to the H is here. So this is in pictures writing what this adjoint action is. So we can still make sense of this idea of topological lines acting on operators. We just need to remember that we have this when we integrate, when we write the charge E, then we need to attach this topological line. But okay, enough with the pictures. Let's go and compute what these spin 1 operators are. And they're a bit of a mess compared to SU2, but we know what they are. So this is an example of a spin 1 representation. I could find many others. Remember, for SU2, it was just sigma plus, sigma z, and sigma minus at a point. Here I'm going to label them by some point I, and the highest weight stays. So this is killed by the adjoint action of E. It's sigma plus at point I, and then has a Q to the H line to its left. So this is simple enough. It's basically what I had before. I just add this line. Now, though, we act with F on the operator, and what we find is, again, something that's pretty simple. So some sigma z operator sitting at some point, but then we have a sum of operators where I have a string starting at some point sigma, some point j where I have a sigma minus, and then it ends at sigma plus where I have sigma at I where I have sigma plus, and I'm summing over all the j's. So you see this has a q in front. So if you send q to 1, this drops out, and then we lower it again, and it gets even worse. So again, here we have a term that's nice, that we have this topological line to the left from some sigma minus, but then we have another term where we have some topological line and you get a point and another operator in a different point, and we're summing over j, and then we have an even worse term where we have a line ending at some point and then starting again at some other point and ending. Okay, this is a bit of a mess, but this is a spin 1 representation. Is this the only one I could find? No, of course, I could find different ones. I could find different representations of this. For example, I could find one where V minus was simple. Well, it was just this, but then V0 and V plus become more complicated. So one question that I have right now is there a better basis where things, maybe they don't all look nice, but they all look passable? Right now, V minus that I showed you before, it's a bit of a mess also for doing computation. So maybe there's a better basis for this. This I'm sure there is.
When you say it's a bit of a mess, it doesn't have any chance to behave as a local operator.
Well, let's see if that's the case. So, okay, so now I want to go and, well, I mean, I shouldn't expect these operators to be local, though. That this is, I know that they shouldn't be local.
Well, they should be
and then,
partly local, right?
Yeah, like this thing, it's a non-local operator in the way that we like it.
Yeah.
And this is not the kind of things that we like.
Yeah.
So, okay, so this is already starting to answer maybe a bit your question of, shouldn't this just be like the free boson? So this, like if I were to remove, as I was saying, let me repeat it. If I were to just get rid of this boundary term, that's just the x-axis spin chain. It's known that a criticality, it's described by a C=1 CFT, which is the free boson at a given radius. If you know what it means, that's great. Otherwise, just some CFT. So given that this is a small thing that I'm doing to this CFT, this spin chain, I have 10 billion sites. Who cares about the first and the last? What you might wonder, okay, like why isn't the physics in the CFT? Why isn't it the same? So from some point of view, we can think of these operators being related to those of the free boson, like V plus is just like the operators that I would normally put there. In the case of the free boson, this would be some vertex operator with some topological line attached. So it just looked like it's an operator living in the twisted sector of the free boson. The rest is a bit of a mess. So I can tell you, okay, V plus looks exactly like what I would expect, but V0 and V minus, they don't look like this. I would need to put vertex operators around and connect them with lines. So maybe not that simple to understand operators, but it's even worse with correlation function. And I think this is what the comment you had before. I'm going to compute correlation function, and now I'm going to say something very obvious, but it wasn't very obvious to me at the beginning. So, but okay, the thing is that the Hamiltonian is not Hermitian. So I have this boundary term, which is purely imaginary. So the Hamiltonian is not Hermitian, which means that the right eigenstates and the left eigenstates, they're not that easily related as they normally are. So if psi is some right eigenstate, psi dagger is not a left eigenstate. That's an obvious statement about matrices. And for example, if I take some operator in this Hilbert space, sorry, some state in this Hilbert space, which is a singlet of the quantum group, so it's killed by E, then it's not a given that psi dagger will be killed by E. So this would not be a singlet of the quantum group. So I need to do things carefully.
Is it diagonalizable?
Sorry?
Is H diagonalizable?
Yes. For generic Q, it's diagonalizable. You might get Jordan blocks for Q being a root of unity.
Spectrum even real, if it's on the so-called Q's on the so-called spectrum even real. Really nice.
Yeah, it's not unitary, but the
Nice,
spectrum
nice.
is all real. That's also important. Thanks. So what happens for this Hamiltonian is that when you take the dagger of this Hamiltonian, you don't get itself, but you get itself conjugated by this matrix X. X is just the product of all the sigma X matrices. This is just a Z2 transformation, it squares to 1. So if we remember, okay, if we know now that psi is a right eigenstate of the Hamiltonian, then it's not psi dagger that will be a left eigenstate, it will be X times psi that is a left eigenstate of the Hamiltonian. In the same way, if I define the bras from the cats like this, then if E kills the cat of psi, it will also kill the bra of psi. And this is where correlation functions differ quite a lot from the free boson, because what I'm interested in is the correlation function of a bunch of operators on the right and on the left vacuum. So when I write O like this, I mean X times X times the cat, which I then dagger. This is the one I'm interested in because O is the cat here is a singlet of the quantum group, but also the bra is. So this is the kind of thing that satisfies word identities. This is what I'm interested in. If I go instead and look at the wrong thing, let me call it just O tilde, if I just take the cat and I just dagger it, this one will not satisfy word identities. So this is not the thing that I'm interested in. But from the point of view of the free boson, let's assume that the physics of these two spin chains in the thermodynamic limit is very similar. If I were to compute something for the free boson, I would be computing this. So these two things, they're not really close to each other because I'm inserting this operator that acts on all of the spin chain. So that's why I think that even though the two spin chains look pretty similar, that we have the conformal data is supposed to be very different because we have different operators, but also what we mean by computing the correlation function is not the same thing. So they differ by a very large operation, which is acting with this X. And now we're ready. I am gonna go over.
Maybe one question. So if I understand, you really constructed, or you chose your family of operators because you really want UQ and sum 2.
Yes, yes.
Typically in a CFT, the way to choose the field is via the state operator correspondence.
Yes.
That gives a different family, or that works with your operators that look pretty non-local?
No, I expect to see the same things from the correlation function and from the state operator correspondence. But the thing I want to look at correlation function, and now I need to, I want to work at a given sector to read off in a given symmetry sector to read off the scaling dimension of operators in that given sector. So from this point of view, it's the usual thing.
So that's the kind of operator that would come up. When you remove a disk, you put a state, and you would get this kind of.
Yes, I think so. I have no reason to doubt that. Okay, so I realize I'm really over time, but so let me just tell you very briefly that we do this computation using numerical methods. That's called DMRG, which means you take a state, which in general has 2 to the n parameters, and then you just truncate a bunch of these parameters away. You make an ansatz for the state where instead of having 2 to the n parameters, you keep something that's linear in n, and here chi is some truncation that you decide, and the higher chi, the better. But the statement is that this is a very smart truncation to do. So if you do this, you can get away with very large system sizes and still get very good results. All of this, by the way, is numerical. There's no rigor on this. This is just doing some variational approach with a smart ansatz. And the answer, and what I'm doing is I am fixing the number of sides in the Hamiltonian. I am fixing Q. And for that given side choice of N and Q, I compute the ground state of the Hamiltonian. And then I place these operators that I consider I'm taking the 0th component. And I'm placing one on some side I and one on some side J, which are symmetric within the with respect to the center of the spin chain. I compute this 2-point function, and then I compute it again at like further away, and then further away, and so on. And I take them all the way until the end of the spin chain. What do I observe? I observe the following. So here you see there's 2 plots. The blue one is the one that you should not compute, but I didn't realize this when I computed, so I just put it as well. You see, if you compute this, you get something that doesn't even go to 0. You want something that decays at large distances, but if you take this correlation function not on the 2 eigenstates, then you get something completely different. What you should consider instead is the yellow line. And this is a log-log plot of the value, absolute value of the correlator with respect to the distance. And you see that it goes in a straight line up to sort of here, which is indeed a power law. This is the kind of thing that we would like to get. Then you don't expect to find a power law all the way to the end because you have boundary effects. But this is sort of as good as it gets. So from this point of view, it looks like we found the actual, the scaling operators. Qualitatively, this is the behavior we want. Now what we need is to do the quantitative. And this is one of the things that we are not there yet. Because, well, there's 2 ways. So I worked at finite n, large but finite n. I'm interested in the n to infinity limit. And in my mind, there's 2 ways of doing this, which are equivalent. So one is from the previous plot at fixed n, I get what the power law is. And then I do it again for a larger n, and then again a larger n as well. And then I take the limit of n to infinity by extrapolating this. This should give me the delta, the scaling dimension of the CFT. Otherwise, I take the spin chain with some n, and I place the operator, let's assume, for example, at 1/3 of the chain and at 2/3 of the chain, and I compute this correlation function. And then I take a larger spin chain and I do the same, keeping fixed the relative position of these operators, and keep on doing for larger and larger n. This should decay as a power law, and it should give me the same power law behavior. Yes?
Can't you have rather one of a sinus of distance to some point?
Sorry?
It should be a sinus, now you have boundaries. So why is it to say power law?
Well, what I'm saying is that I should look at a region where I'm not close enough to the boundary so that I still see a power law.
The previous plot you looked come pretty.
Yeah. I mean, numerically, once I compute this, there's the hard part is to compute the state, and then it's not too bad to actually compute this. So I went all the way until the end.
Does it fit well with the 1 over sinus?
1 over sinus, I didn't try.
It's 2-point function on the strip. I mean,
That's fair.
you shouldn't fit it with a power law. So,
That's a fair point. Yeah, I didn't do that.
Sorry, but you want to be sure that you want to be sure that your fields are bulk fields, right? In the bulk.
yeah.
Yes.
Well, how you control it that it's not converging to a boundary field, or because it's finite lattice? Then how can you distinguish between boundary and bulk? The spin chain is open, right? It's boundary conditions. Yes. How you distinguish between bulk and boundary?
For the operator, if it's inside the chain, it's a bulk field.
That was my approach. Yes. The boundary fields, to look at correlation function of boundary fields, I would put them on the boundary, and then I would need to evolve with time and do something like this, right? Here I'm just looking at like the Hamiltonian is there, and I'm looking at things on the Hamiltonian, so I'm keeping, time is fixed. I'm just looking at things that move within the spin chain. So to me, this looks like a bulk field.
But if I always increase n and I keep field like 2 sides out of boundary, the scaling limit is basically on the boundary, right?
Yeah, but that's not what I want.
That's not what you're doing.
Okay. So yeah. So we try to do this for n to infinity, and for now, the numerics sort of depend on what you do, which means that they haven't really converged, which means 2 things, at least one of 2 things. Either we're doing something wrong, which I hope is the case because that's solvable, or this is one of the cases where you have large corrections to the thermodynamic limit, like in XXZ, because you have some operators close to marginality. And then to do this properly, you need to be pretty smart. But the statement so far is, okay, we build operators that transform well under this quantum group and that behave as a power law as we go to larger and larger distance. So this makes us believe that we've identified a microscopic description of this field, and these topological lines that we were saying that should be there, we can observe them exactly in some case. Any question on this? Yes.
You do with your bond dimensions that you take and bigger.
So because
really what you're doing, you're scaling in both n and in bond dimension. So
yeah, so what we do in practice is we keep like the cutoff of which principal value you throw away or not fixed, and then we increase the bond dimension if it's needed. But like, yeah. So the bond dimension is normally it doesn't appear to be an issue, as in we keep.
I give you some finite correlation length.
Sorry?
The correlation length you can get in the state is bounded by.
Yeah, but normally we keep up like the maximum bond dimension is very high, and then it's just a matter of the cutoff of like what we throw away. So I don't know how to interpret the cutoff and
it actually helps you because you cannot see if the correlation length is smaller than the size of your system. It's as if it's infinite because it doesn't see the boundaries of it. So it's actually
I see.
And well, the better thing to do would probably you can do these things directly in thermodynamic limit, and then you don't have to worry about it.
Yes, but then the issue is that I don't know how to use the other packages.
Oh,
That maybe you will be helpful for this. And this is not Hermitian. So there are some packages that you can just say this is not Hermitian, and they tell you what the ground state is, and I don't know about
that's so problem.
No, so how can you do directly thermodynamic theory that you need to have access to the boundary?
Why do I need access to
This is infinite volume.
I'm looking at different operators though.
Volume MPS.
Yeah.
That's very different. That's very different calculation. You just take one single term of the Hamiltonian, you minimize the energy, but that's not what you're doing here.
That's not, no. Here I'm doing finite.
You really have to define it, otherwise you're going to lose this quantum symmetry.
No, the only thing that's important is that this local term of the Hamiltonian has a quantum group symmetry. So Bernardo has this local term where you just have sigma z I minus sigma z I plus 1. And then indeed, if you sum this only is something on the boundary, but you can define a local term that is quantum group symmetric. That's enough to do it in the infinite case.
So yeah, I'm gonna write this explicitly.
And the important thing here is that here you cannot minimize the energy by a local calculation. You cannot find the ground state just by picking one term of the Hamiltonian and of minimizing that term. It's just going to give you wrong result. It's going to give you XXZ spin change.
No, but in the thermodynamic limit, the energy per site will be the same between this and the XXZ spin chain. The question then is, well, like I think that the issue is actually, like looking at the operator I'm talking about. That's probably the issue with the infinite dimension thing. I need this topological line to go up to somewhere. I need to sum over things. I don't know how to deal with that. Maybe that's doable.
That's okay.
But I think I could do this. If that's not an issue, then I think I would be able to.
But can you say something? So you mentioned there were these ground states.
Yeah.
Maybe on the previous slide. I don't know. Maybe you should finish because we seem to be.
Yeah. I'm definitely over. What time did I start?
Started roughly an hour ago, but go for 10 minutes.
I think I started. I still have 5 minutes.
Yeah.
That's
At
true.
least 5.
So I'll take 10 or 15 in total from now. If that's somebody cancels their talk, right? So there's a long time before dinner. Okay, so let me talk about a different model now, which is the one that Sasha discussed, the continuum limit. And I can write the Pascal Hamiltonian, the one I just told you, as a sum of these terms that I call Ri, which is, okay, this is just the XXZ terms between site I and I plus 1. And then I have this term here, which is sigma z on site I minus sigma z on site I plus 1 with this purely imaginary term. So I can write this, the Hamiltonian, as the sum of this because, well, all these terms I keep, I want them. But this will give me a telescopic sum where I can only have, well, I will only be left with the first and the last term. So that's nice to write it like this. It's not necessarily, well, it's not necessary, but it's nice because these RIs, they are generators of a Hecke algebra, which is some algebra that has these properties. And they are closely related to the temporally Lieb algebra, which if you take Q minus this RJ, that gives you the temporally Lieb generator, which we all know and love, or maybe we don't know it, it doesn't matter. This is a way of writing this Hamiltonian in terms of just this algebra, this temporally Lieb algebra. And the interesting thing about this RI is that they all commute with the quantum group. So you can check this explicitly, and then it follows that the Pascal Hamiltonian commutes with the quantum group. Now, this is almost like open boundary condition, as in there is no, what I mean by this is there is no interaction between site I and site N. We like, in physics, we like to work with periodic boundary conditions because they had system with that, they had translational invariance, that's another symmetry, we like symmetry, so we have a better handle on the system. So can I build a model, maybe starting from this and changing something so that it has both UQSL2 symmetry and periodic boundary condition, as in translational invariance? Let's see this.
Why don't you just sum this over the whole?
That's what I'm gonna say, and there's a naive here. So the first thing I could try, so I told you these are n's, I've defined them from 1 to n minus 1. I haven't defined the nth one. No, wrong side. So let me define the Rn as just those, but translated by 1, where I make the identification between n plus 1 and 1. So here I have an interaction between n and 1. So this is exactly what I would do if as the first try. But you can check explicitly that this thing does not commute with the quantum group, which makes sense, because if I were to sum over all of these Rn's, then the telescopic sum cancels completely. And this tells me that I had the XXD model with periodic boundary condition, which doesn't have quantum group symmetry. This is something that it's known. It just has a U1 symmetry. So this doesn't work. I need to do something smarter. And when I say I say that these authors did it. So you can define this operator G, which is the product over all the Ri's. And the action of G on one of those Ri's, you can check thanks to the properties of this Hecke algebra, shift this Ri by 1. So you act on Ri and you get Ri plus 1. Okay, so what I'm going to do is I'm going to define Rn as the translated Rn minus 1. So I act on Rn minus 1 with G. And then by construction, this Rn is symmetric under the quantum group. Because of all of these R's, they commute with the quantum group. The only thing I need to check, and you can go and check it, is that then acting again with G on Rn goes back to R1. And that's true. So nice, we found something that I'm gonna call it XXZ spin chain, which is just the sum over now all n of these Ri's. Okay, so that's, I'm gonna call it as HQ. What are the properties of this? It's quantum group symmetric. It commutes with G, with this operator G, because G just cyclically shifts these Ri's. So it doesn't do anything to the Hamiltonian. And I told you what the Ri's are. I didn't write Rn because it's a mess. It's a very non-local operator. It looks as complicated as the operators that I told you. So it's a bit of a mess, but it's something, we have an expression for it. Okay. G, you might say G is a translation operator. It is a translation operator if you look at the right things, as in on these Ri's and in general on things that transform well under the quantum group. It acts as a translation by 1. But if you take, for example, some sigma matrix, it will not act as a translation on the sigma matrix. So it's not exactly translations, but okay, it's still a symmetry of the Hamiltonian. And this spin chain is critical, and it's known that it gives this CFT with this charge, which is smaller than 1. When I parameterize Q like this, it gives this C, and this is the one that we knew the spectrum of and we studied. We don't want to do DMRG here because DMRG works not as nicely when you have periodic boundary condition, but we're gonna consider a few other things here. The important thing is that G is a symmetry of this Hamiltonian, and the ground state is invariant under G. So if I take, for example, some correlation function of operators. I can put G and G minus 1 between every operator, and the one acting on 0, they will drop out. And this, so basically this correlation function will be equal to this correlation function. And if I take some operator that transform nicely under this G, then I get translational invariance. So like this VI's operator, when the one I told you earlier, when I act with G on it, these are shifted by 1. So VI gives me VI plus 1. So this is great. If I go and look at a correlation function of these V operators, this will be translational invariant in the sense that I can shift all of them by K sides and I get the same correlation function. So this is what I normally would call translational invariance, but only if I look at this operator, not if I look, for example, at Pauli matrices. In that case, this would not be translational invariance. So it looks like we have some sort of translational invariance. Is it really periodic boundary conditions though? That's unclear. I don't think it is, but let me tell you why. The reason is that when we act with so Gx as a translation, the VIs, if I stop just before n. When I act with Vn, this will not give me V1. So while with the Rn's, the action of G would just go around the circle, here on Vn, this doesn't happen. And there's two options that I see. One is that I told you that there's some sort of ambiguity in which basis of operator should you choose. Maybe there's a better basis for the VIs. Let me call it V hat, so that this actually works in the same way as the Ri. So also acting on Vn gives us the V1. Maybe there exists such a basis, and then I would call this periodic boundary condition. Probably not, though. That's my guess would be that it's not the case. So we can think of this maybe as having some topological defect inserted between site n and site 1. A topological defect would make sense because we have a correlation function that I can move around, and as long as I don't cross the defect, then nothing changes. So I'm just free to move around and the correlation function is the same. But when these operators cross the defect, I don't expect to find the operator at 1, but I would expect this operator to find the operator with the action of the defect on it. So this looks a bit more likely to me to have some sort of twisted boundary condition, but this is one of the things that we're not sure about yet. And it's the fact that when you actually do this computation, you get a mess. And I don't know how to make sense of this. But this is one of those questions. Yes?
It's kind of localized around 1 and n, or is that
No.
so it doesn't look like it's...
Yeah, but like the thing is that I wouldn't say that the operators that I'm working with are necessarily localized around 1 and n to begin with. So, you know, this is a bit of a mess. Maybe there's a basis in which I can see that the amount of messness it's preserved when I go around the defect. Maybe, I don't know, or maybe, but the thing is that as long as I don't cross this boundary, correlation functions are translational invariance, which really suggests that it's some sort of topological thing that I'm doing on this between these two sides. So not to have an explanation for this would be a bit annoying, I would say. And now I will tell you the last thing, and at this point, these are open questions. The one after, it's more of a like, I felt taken, I felt like he was playing with me, this model, given the next computation. So I think it's more likely to have exactly this topological twist because we know the partition function on a torus. And this has been computed. This was, you know, just, these are the characters, the partition function is, you know, the characters, holomorphic and anti-holomorphic, and they have some multiplicity, and we know this. And well, the partition functions, if I have a periodic boundary condition case, then this partition function, I expect it to be modular invariant, so the tau is invariant under SL2Z transformation, and especially under an S move, which is taking tau and sending to -1/tau. A way in which I could break this modular invariance is to insert a defect. For example, imagine I have my very well-behaved CFT, like the easy model, and I put some topological defect in one of the cycle of the torus. When I do this S transformation, then this defect goes from being on one of the cycles to being on the other one. So if I insert some topological defect, I get something else, and it's not modular invariant. So we know what the partition function of this theory is. Let's go and check if it's modular invariant. So this is the partition function. And we checked it, and it's not modular invariant. So it looks like there's, one way of seeing this, one way of explaining this would be that there is some topological twist inserted. So this is one idea. What could you do to check that instead, like to check what this twist that you have inserted, what is it? You could try, if you have, let's say your twist is inserted vertically, try to insert the same twist horizontally, and then under an S move, the vertical one becomes horizontal, the horizontal one becomes vertical, but you should get the same partition function. So under an S move, if I insert the right defect, then I should find something which is invariant. So let's try to do this. There's not many things that I know how to twist by. It's just Q to the H, the one that I know how to twist by. So we can compute this. And then what we find is that once we compute this twisted partition function, it's almost invariant under S. What changes is that you get the same partition function with Q and Q bar swapped. I don't know what this means. I don't know if this means anything at all, but this is a very confusing thing to me.
And your model does not look invariant if you just reorient your circle.
Yeah, so Q, it's not invariant under
left-right
Q.
symmetric.
Sorry?
It's not in left-right symmetric.
It's not. It's not. So, I mean, if it was, I would be done, but it's not. So maybe, yeah, I don't know. Maybe I'm trying to do the wrong computation. This is clearly it's not a Q to the H twisting that I'm doing, because I know what a Q to the H twisting looks like, and it's not that messy. But what we're trying to understand is, if it's a topological twist, then what is this twist? So this is something that we're still, I think, not very close to understand. With this, I conclude. Let me sum up what I said. So these operators that in this UQSL2 symmetric CFTs and in these UQSL2 spin chains, they're definitely non-local in the terms of sigma matrices, and they come with this Q to the H or Q to the minus H tails that are topological. We've looked at them on the lattice and computed their correlation function for large distances and see indeed a power law behavior. And this look somehow related to twisted sector operators, U1 twisted sector operators of the free boson, but the correlation function looks very different from this. What is there to do? We need to finish this numerics. We would like to probably understand if there's a nicer basis of operators to work with, both for the numerics and for this story about the twist. I didn't discuss this, but this model that I'm studying is actually integrable. So we're doing the MRG because we don't know how to do integrability, but maybe we should learn how to do integrability and understand if the computation of these 2-point functions with these very non-local operators is something that it's doable under integrability, and then understand the story about how to understand these boundaries in the XXQ case in terms of a topological. Thanks a lot.
Thanks much for the nice talk. We have time for questions. Ingo?
I feel it's a bit similar to something which Bajanov, Lukyanov, and Zamolodchikov did a while ago, where they took a free boson with a background charge, and then they have a construction that can be interpreted as putting some topological defects in that model and then deforming it by something related to UQSL2. Is that, I mean,
I'm not sure I know that. Do we repeat the names?
Bajanov, Lukyanov, and Zamolodchikov.
I think it's something that I've met, but I don't have a, I don't know. Maybe Sasha, you know something?
I remember their construction is chiral.
So you can make there's a version of it which works with a full theory, and maybe it's for later, maybe not.
I agree that also this issue of the cat with zero and the cat with a dagger, that's also reminiscent of background charge phenomena.
Right.
Yeah, so we also have the Coulomb gas calculation of these correlators. This is what we didn't talk about in none of the two talks. But yes, with this Coulomb gas computation, we also add a background charge. But then we need to modify the Coulomb gas a little bit. Yeah, we can discuss more details later.
The partition function invariant and the tau goes to tau plus 1 or not?
No, because the spin is non-integer. So it's not. But I wasn't requiring that. I was requiring something that in my mind it's less than that. But that again, that tells you that you shouldn't expect translational invariance. It's natural to expect something inserted in your yeah, exactly.
But you were mentioning these issues in the numerics, and you said, well, maybe this is corrections to scaling. Like, of course, if it were a normal CFT, it's a very simple question to figure out. If you know the spectrum, you know the spectrum. But here, even your partial information about your theory, do you know if there are if there's something that you can call marginal perturbations?
Well, there definitely are close to Q equal 1. Well, at Q equal 1 there are. But then the question is, as we move further away from Q equal 1, if they're still, close to, well, actually it's Q minus 1, but it doesn't matter. If like they move away from this, but the question is how bad, like how quickly they move away from it. So I don't know. There is something to explore here.
Is there a notion of bulk scaling dimensions for these theories?
I think what we're looking at is that it should be that.
And do you know bulk scaling dimensions of these theories?
No, we know the boundary ones.